Okay, the next topic is continuous random variable. Actually, it's not very different, except that we use the concept of PDF instead of PMF. What is PDF? PDF is the derivative of PDF. PDF is the derivative of CDF. In other words, CDF is the integral of PDF. Unlike the PMF case, where the PMF has a meaning that in the discrete case, f(x) of s means probability that x takes value s. And in the discrete case, when s is in the support set, this is positive. However, in the continuous case, probability that x is s for any value s is 0, and the underlying intuition is this: probability that x is s is total number of cases over number of cases that x is s. When x is a continuous variable, the total number of possible cases is infinity, and the number of cases that x is s is just 1, so it's 0. That's the most intuitive understanding why when x is a continuous random variable, this point probability is 0. This is not actually quite correct. Why the point PDF, the point probability is 0 in continuous case, because in the discrete case, there are cases that the number of possible cases is infinity, yet in the discrete case the point probability mass is non-zero. But I guess all that matter here is the fact that point probability when your random variable is continuous is 0, and you have to distinguish the PDF from the probability interpretation. Whereas when you're dealing with discrete case, the PMF is has an interpretation of point probability or probability mass at a point. From now on, I'm not going to distinguish between PDF and PMF, and because PMF is in a sense a PDF. So without telling you why further, I'd like you to accept that at least for the convenience of a notation and expression, I'm not going to distinguish PMF and PDF. I'm going to call them, both of them, PDF. Okay. Expectation now becomes integral. Okay. So in the discrete case, expectation is the summation of value times PDF. Now when x is a continuous random variable, it's the integral times value times PDF. Okay. Right. The multivariate continuous random variable. For multivariate continuous random variable, the CDF has the same meaning. Okay, so this is in a sense probability that your x is less than S1, S2 up to Sk, right? And the PDF here is kth order partial derivative. Okay. This is your joint PDF. From this joint PDF, you can construct marginal PDFs. Here in the continuous case, your marginal PDFs are derived from integral, not from summation. But other than that, conceptually, nothing is very different. Conditional probability the same. Okay, it's the joint divided by marginal PDFs. Okay. Moment, nothing special. One thing that you have to keep in mind is a multivariate random variable can be continuous in one coordinate and discrete in other coordinates. For example, consider a random variable x1 and consider a random variable y and x where y is a discrete and x is a real number. Okay, so it is possible. In fact, if you recall, the usual linear probability model is one of these cases. Suppose this distribution model where y is binary, so yes or no, pass or fail, and so on, and x is just a continuous random variable. So maybe study hours of studying. This is success or failure at an exam. Then the joint random variable y and x is continuous and this is discrete, actually binary. Okay, so it is possible that in a multivariate random variable, some part is continuous and some part is discrete. In this case, you may not the f function, lowercase letter f, is defined by this partial t probability that y is s and x is less than or equal to t. That's the PDF. Okay. Okay. Transformation. So if your y is a function of x, okay, your y is a function of here. This g is vector value function, possibly. So there's this the the G maps a k-dimensional vector to m-dimensional vector, or since we are talking about random variables, G maps a k-variate random vector to an m-variate random vector. So here, this y is m-dimensional, right? And this x is k-dimensional. Okay, then the probability of y less than t, here this is a vector and this is vector as well, right? So this less than or equal to is in a vector sense. So this means that y1, y2 up to ym is less than equal to t1, t2 up to tm, which means probability that y1 less than t1, y2 less than t2, and so on up to ym less than tm. That's what this part means. Okay, and you are going to take partial derivatives, m times partial derivative, nth order partial derivative, and that's your PDF of y, and that's this, right? That's this. This, sorry, I believe this is smaller than t. Okay. All right. The simplest case is when this this transformation G is linear. Okay, suppose your y is 8 times x, and A is a full rank matrix, square matrix. Then show, this is an example, so you need to prove this. The PDF of y can be written this way. Okay. Okay, property of moments. Here I'm saying the integral could be the multiple integral. So here, this integral may mean integral up to integral g of s1, s2, sk, fx s1, s2, sk, ds1, ds2, dsk, right? Keep in mind that when you read this part, the integral here may mean multiple integral. Okay, first property of moment is it's linear. It's linear operation. So okay, and expected value of x and y, which is what? Which is this one is integral xy times f xy dx dy. That's what this is. And what is this? This is integral x fx dx times integral y fy y dy. So these two in general are not the same, but if fxy is fxx times fyy, i.e. independence, statistical independence, then this now becomes an equality. Okay, another very important property of moment is law of iterative expectations. So here, this expectation, so let's change the variable. Expected value of y may be computed by double expectation of y given x here. So you take the expectation of y given x first, and then takes the expectation again. That's gonna give you expected value of y. Expected value of y given x and z. If you take the expected value of y given x and z given x, it gives you expected value of y given x. Okay, and then expected value of g of x given x. Given x means x is no longer a random variable. So g of x given x is no longer a random variable. Therefore, expected value of g of x given x is just a g of x. Actually, this notation it may be a bit tricky for you. So it means actually this expected value of g of x given x is, let's say s, is g of s. Okay, that's what this means. Variance of g of x given x is s. So when x is s, g of s is just a constant. So if the variance of a constant is 0, and that's why this is the case. Okay, show this. Next time I'm gonna talk about some important